In the world of towering telecommunications, every bolt, nut, and washer carries a critical responsibility. Imagine the strength and stability of a massive tower relying on these tiny yet mighty components. Bolts play a crucial role in telecommunication towers, providing stability and security to the structure. A single failed bolt can have catastrophic consequences, including tower collapse or equipment damage. But how do we ensure they are up to the task? To ensure our bolts meet the required standards, we conduct a range of tests. In these tests, the fasteners undergo rigorous real-life simulations. These tests include 1. Hardness test. Hardness tests measure how well a material resists indentation or penetration. Essentially, this tells us about the bolt or nut's ability to withstand surface-level forces without deforming. It's a vital property for components that face constant friction or compression during use. The obtained values from this test are as follows. 2. On the other hand, tensile tests evaluate how much axial load a bolt or nut can withstand before breaking. This test is crucial for applications that involve pulling forces. Results of this test are as shown. 3. Shear test. The shear test examines the ability of a material to resist forces that cause its layers or components to slide against each other, such as in joints, where components experience lateral motion. Why are these tests so important? Imagine how catastrophic a structural failure caused by a weak bolt would be. Hardness testing ensures the material can withstand wear and compression. The tensile test measures a bolt or nut's ability to resist axial pulling forces, while the shear test confirms it won't fail under sliding forces. Together, these tests give us a complete picture of the component's reliability. In order to be able to use these bolts for the said project, a telecommunication tower, it is necessary that we compare these values to the relevant standards such as ISO or ASTM standards. During the tension test on the 8.8 bolts, both of them failed miserably as their nuts slipped due to lack of hardness of the bolts. The values from hardness and shear tests of 8.8 bolts were also not meeting the requirements. In contrast, the tests on grade 5.8 bolts were satisfying the standard values in shear, tension, and hardness. The only concern we had was the slight exceeding in the values of elongation and reduction in area as compared to standard. So we can conclude that both the 8.8 bolt specimens were substandard and had to be rejected. As a result, the grade 5.8 bolts are to opt for as they comply with standards. This procedure helped us to grasp the nature of a real-world problem in the field of civil engineering, highlighting the importance of practical data along with industry standards. Thanks for watching.